So thanks for the introduction. Thank you as well for everybody at VSpark for organizing this summit. So my name is Ruud Kortlever. As Ike mentioned, I'm an assistant professor at TU Delft in the Department of Process and Energy, to be exact. And today I would like to discuss a bit of the TU Delft approach around electrocatalysis and electrosynthesis. And I'll do that in two kind of ways in my talk. So first, I'll introduce a bit on the approach that we have as TU Delft in a whole, which we call the e-refinery, the TU Delft e-refinery initiative. And then I'll also show a bit of examples from where my group is working on and the approach that my group is, or our group is taking in this research field. So my talk is entitled "How a Multidisciplinary Approach is Key Enabling Electrosynthesis Techniques," and this is really what we're trying to do within the e-refinery initiative in TU Delft. So as all of you know, there's a lot of fuss, of course, to reduce the CO2 emissions, right? We want to mitigate climate change and all of the repercussions that it has. So as you know, there are multiple multiple agreements now in place. The Paris Agreement in the Netherlands, we have the Klimaatakkoord to reduce the CO2 emissions. And to try to go from a fossil fuel-based society towards a more renewable energy-based society. And this picture shows some people demonstrating and saying renewable energy is the solution, and I completely agree with these people that renewable energy is the solution. But unfortunately, as probably all of you know, it's not as easy as that, right? So renewable energy sources are, of course, intermittent. The sun doesn't always shine, the wind doesn't always blow, so we need to store energy on a large scale. And on the other hand, we have a lot of products at the moment from the chemical industry, things that we see around us that are made from fossil resources. And if we want to change from fossil resources to a more renewable resource-based society, then we also need to switch that, right? So, this picture, I think, is a good summary of how electrocatalysis, I think, can play a big role. I like this picture a lot, especially because it puts electrocatalysis in the middle. It's from a paper from Tom Garmillo and Jens Norskov's group. Where you can see that we can couple these renewable energy resources, the energy inputs from these renewable energy resources, and use the electricity from the sources with electrocatalysis to convert, for instance, nitrogen, CO2, or water into valuable chemicals, right? And that would be, for nitrogen, would be ammonia, and ammonia, of course, is a resource for artificial fertilizers. But in the future, you could maybe potentially also use it as a liquid fuel. You can convert CO2 in hydrocarbon products, and thereby using it as a carbon building block. And of course, you can split water into hydrogen and oxygen, which you then, of course, can also still use in the chemical industry, or hydrogen maybe also as a fuel. So there's a lot of things that are possible with electrocatalysis. And electrocatalysis, I think, might be able to play a very big role in this energy transition. If we look at the options, right? If we look at the options that the industry and society has to reduce CO2 emissions and reduce greenhouse gas emissions, there are a couple of them. So it's increasing energy efficiency, implementing CO2 capture, for instance, using heat integration, using biomass as a feedstock. And in the mobility sector, you can think about electric driving or hydrogen driving. But within the e-refinery institute at TU Delft, we focus on two main routes, which we call an indirect route and a direct route, to produce chemicals and fuels. Where the indirect route is coupling water electrolysis, so water splitting to form hydrogen and oxygen, to conventional thermochemical processes. And the direct route is direct electroreduction with electrocatalysis of CO2 and nitrogen into these products that I mentioned before. Yeah, and then the overall goal as an e-refinery is really to accelerate this transition towards sustainable production of chemicals and fuels. And we really like to do this together, of course, with industry, together with research institutes. The person after me, Anka, is going to talk about what TNO and Voltachem is working on. So there's also there's a lot of collaboration and contact with them. So we really try to collaborate with a lot of people, either from industry, academia, research institutes, to try to accelerate this transition towards a sustainable future. Yeah, so I already mentioned these two routes, the indirect route, the direct route, and I would like to show you a bit more on what I mean with this. So in the indirect route, we take electricity, we take water, and we either take CO2, nitrogen, or a biomass as a feedstock. We first use the renewable electricity to split water into hydrogen, and then we couple this hydrogen and these feedstocks into chemical processes and produce bulk chemicals that you can then use for the process industry or as fuels in the industry. And of course, all the wastes of this, the usage should be recycled again to close this loop, right? So the way that you can envision this indirect route, for instance, is using hydrogen, renewable hydrogen, so green hydrogen in that sense, in Haber-Bosch synthesis to produce ammonia, or also, for instance, in Fischer-Tropsch synthesis to produce hydrocarbons. So instead of using hydrogen from fossil-based resources, so from steam methane reforming, for instance, we really use hydrogen that was generated from water splitting with renewable energy, so renewable electricity. And the challenge here, of course, is really still integrating the electrolysis processes into these thermochemical processes. One thing that you can, of course, imagine as well is that what I mentioned before, renewable energy sources such as solar and wind are intermittent, right? They're fluctuating. Well, these thermochemical processes are 24/7 processes, right? They're running the whole day constantly. So how do you couple a steady state process with an intermittent process? So these are all challenges that need to be looked at. Now, for the direct route, as mentioned before, we again use renewable electricity. We use water, CO2, nitrogen, and then we directly convert the CO2, nitrogen, or biomass, for instance, with water and renewable electricity into bulk chemicals. And the same applies, of course, that if upon usage, you should again recycle your waste and emissions from usage to complete this cycle. So the way that we are looking at it as e-refinery in TU Delft is that we're trying to address these processes at different scales. So really from the micro scale, so the design of the electrosynthesis processes, to a meso scale, so engineering reactors, process system designs, process conditions, to really the macro scale where we do techno-economic analyses, life cycle analyses of these kind of new processes. So really trying to tackle this problem from multiple scales. And if you do so, you of course need many disciplines. So there's a lot of expertise and different expertise necessary to look at these different skills. And it's all, of course, applied on these two research lines that I mentioned before. And the overall goal, of course, is to produce these base chemicals and fuels, right? So if you look at the disciplines, there are many disciplines ranging from chemistry, chemical engineering, so the electrochemistry side, catalysis and electrocatalysis, up to the reactor engineering, the really hardcore chemical engineering side. But also, of course, you need to think about the integration of renewable electricity. So there's electrical engineering involved, part of mechanical engineering, and of course, there's also the real process system engineering involved there. So what we're trying to do is we're trying to couple people with all of these expertises together, and trying to in that way try to talk, get them talking and accelerate the way that we can develop these processes. So maybe a bit on the research goals that we have as an e-refinery. So we've set a couple of goals for ourselves to achieve, hopefully by 2025. We realized that if we want to have a successful transition towards these new technologies, then we have to act fast. So for the indirect route, there's an electrothermochemical kind of pilot that we want to build, where we have a system that effectively or efficiently produces methane with a Sabatier reactor, and combines then water electrolysis to hydrogen with the Sabatier reactor. For the electrochemical system, we aim at a 100 kilowatt system for the conversion of CO2, direct conversion of CO2 into ethylene, would approximately yield 40 kilograms of ethylene per day in such a device. So that's already quite a big step. And then we have another route where we do a bioelectrochemical direct synthesis, where we use bacteria and redox active bacteria to convert CO2 into hexanoic acid, also going towards a 100 kilowatt system. And these are all kind of systems where we've concluded in discussions with industrial partners that if we can show these or demonstrate these systems at these scales, this is really something that they can further scale up in their research and development activities. So again, here is a bit of a overview of the scales that we're aiming to address. So that we're looking at. So really from the molecular scale up to the plant scale. As I mentioned before, there's a lot of researchers at TU Delft involved, from chemical, mechanical, electrical, materials engineering, policy and management experts. And of course, we link a lot with industrial users, but also we try to have we try to reach out with the global community, so the community in the Netherlands, in Europe, and globally, to work together and to collaborate and to speed these processes up. Okay, so this was a bit of an idea of what e-refinery is working on, and also I wanted to give you a bit of a flavor of the scale of this challenge. So this is taken from a paper from Wilson Smith, a former colleague who was working at TU Delft, who did with a couple of other colleagues, did a couple of back-of-the-envelope calculations on how a 10,000 ton per day methanol plant completely run by renewable electricity and CO2 captured from the air would look like. What would be the requirements for such a plant? So you can see already a bit of how much solar PV area you would need. So it's 243 square kilometers, and that's compared to the biggest solar park that we have now. So it's orders of magnitude bigger, right? So the amount of CO2 air capture cross section that you would need to capture all the CO2 to convert that into methanol, the electrolyzer catalyst area, and this is all compared to what is now state of the art and biggest kind of systems that we have at the moment. So you can see that even for such a methanol plant, which is not even a very big methanol plant, I think it's quite an average size methanol plant, we have to make a lot of steps in these technologies to enable such a large scale facility. So there's a big challenge, and there's a big challenge ahead of us, and I think that's also exciting to work on and see how this field evolves in the coming years. Yeah, so the last part of my talk, I wanted to give you a little bit of flavor of the research that we're doing, and I'll use my own group as an example of research that we are doing within the E-Refinery Institute. So this is an approach that we have within our group. So we have also, in that sense, a multi-skill approach where we look at different skills of electrocatalytic processes. So we try to look at mechanistics and spectral electrochemistry to kind of see what, how these electrocatalytic processes, how they run on the atomic scale. With these insights, we try to develop better electrocatalytic materials. I'll show you a bit of the work that we're doing. Of course, these electrocatalytic materials will only work optimally under optimal process conditions. So there's a part of process conditions and optimizations there. And ultimately, we would like to integrate all of these electrocatalytic materials and the process conditions into prototype devices that can do these conversions. So an example of the work that we're doing on the mechanistic side, this is a recent work from a former postdoc in our group, Andrew Morrison, who looked at a general DFT method to predict CO2 reduction selectivity. There's a lot of work already out there on DFT methods for CO2, trying to get more insight into reaction mechanisms. But what we found is that there was no general DFT method that could predict the CO2 reduction selectivity, so the selectivity of which products we make on which materials. There was no DFT method that could predict the selectivity of a lot of materials, right? So there's no general method to predict the selectivity of all those materials. And what we set out is trying to see if we can find a method that could actually do this. Because if we have a method that could do this, it could also help us, of course, in trying to predict or trying to extend that method and predict if we can or what kind of new electrocatalytic materials might be better for making certain products. So the way that Andrew tackled this is trying to look for what kind of things weren't included in the DFT methods that have been used up to now. And what he found was that one thing that a lot of the DFT methods did not take into account was the surface coverage of reaction intermediates on the surface. So here you can see the insert of this graph. You see the surface, and you can see three different modes of surface coverage, ranging from low surface coverage to high surface coverage. And what he did is basically trying to calculate the energies of adsorptions of these intermediates as a function of the surface coverage. And he found out that it scales quite linearly with the surface coverage itself. And the slope of this line was very characteristic for the selectivity of the material. And by looking at the slope of this line, we could actually categorize the materials, and we could predict what kind of products these materials would make. So you can see here you can see categorization, where you can see that we are able to predict that these metals make formic acid, which is indeed the case. These metals make CO. Predominantly, zinc is a little bit in between. These metals make a mixed kind of a mixture, so mostly hydrogen, but also CO. And copper is in between, which makes C2 hydrocarbons or other hydrocarbons. So this is a first method that was actually able to do this, to generally predict the selectivity of all these monometallic catalysts for CO2 reduction. And what we're trying to do is now trying to expand this and trying to see if we can also use this method to predict new materials that might be even more selective to certain products, and trying to devise new.
I just want to give a heads up that we are past the 20-minute mark.
Great.
It'd be great if you could wrap up with the last few slides.
Yeah, and then I'll go quite fast. So a bit of the work that we're doing as well on electrocatalytic development is trying to develop new materials. So one example there is bimetallic catalysts that we find very interesting. So this is an example of a gold palladium electrode that was able to do to reduce CO2 to hydrocarbons, so C1 to C5 hydrocarbons, which I think is very interesting. So might lead to maybe electrochemical Fischer-Tropsch processes. Another thing that we're trying to do and we're working on is carbon electrocatalyst for CO2 reduction. So this is work from Shilong in our group, who uses nitrogen-doped biomass-derived carbon for CO2 reduction. You can see that depending on the synthesis method, we get very different Faraday efficiencies and selectivities towards CO. So there's a lot of work that we're doing on that. We look at altering product selectivities by process conditions. So this is work from Maria in our group, really working on the electrolyte selection, which has a big effect. Yeah, also looking at high CO2 pressures for CO2 reduction, and ultimately we would like to also do this for nitrogen reduction. So this is a device where we can test up to 100 bars. Yeah, maybe I'll skip this for clarification. So maybe I'll just wrap up with the takeaway messages. So I hope to have shown you that within e-refinery and TU Delft, we really try to do this multidisciplinary. Within our group, we also try to do this at different scales. So I hope to have given you a bit of a flavor of what we're doing within e-refinery, what we are doing within our group. If you're interested, I, of course, I'm willing to, of course, answer all the questions that you have, and you can also always contact me after this this webinar. Before I finish, I would, of course, like to thank all the people that are working on this within our group, and all the people that finance the research that we're doing. So with that, I would like to wrap up. So if there are any questions, I will be happy to answer them.
Thanks, Ruud, for this nice overview of what e-refinery is doing and showing the different angles that we need to solve to really make this a scalable and useful solution. So the floor is open for questions from the audience. So again, unmute yourself, do a short introduction, who you are, and you are free to ask your question. It's nice that you also showed the example, Ruud, of DFT calculations, so doing computational modeling. That's something that we don't have as a strong point in this summit, but that's something that we will introduce also in September, because also computational modeling or trying to predict better is definitely something that is boosting this field. In the Netherlands, we had this enormous bag of money going now to quantum computing development. 600 million in total, even more. So I'm hoping also that we can include quantum computing calculations in this in the near future to speed up or improve the predictability.
Yeah, especially the possibilities that you now have of machine learning, right? So if there is a good way to kind of predict adsorption energies, for instance, which if you can couple it with machine learning, you can maybe speed up the screening by orders of magnitude, right? So that would be very interesting.
That's already something that we from Material Pioneers are working on together with Cytrin Information and Material Zone, two companies that are working on these type of software solutions to help researchers adopt machine learning algorithms quicker and more precise. So there's definitely a lot of room to gain in that area. Still, I think we will be dependent on good measurements, and that's also why these measurement tools are needed. I see a hand coming up, so please feel free to unmute yourself.
Hello, thank you. That was a really interesting talk. I'm Manpreet. I'm a first year PhD student at the University of Warwick. I just wanted to ask if you do anything about any research into nitrogen reduction. I think you mentioned something about pressures. That's my project.
Yeah, actually we do. So we have, together with Professor Fokkel Mulder at TU Delft, who is in chemical engineering, there are some projects on nitrogen reduction. Within my group, we also have one project on nitrogen reduction. So yeah, we're definitely working on that. I think that the main challenge really still lies in the electrocatalyst. So we're still really looking for a material that can convert nitrogen to ammonia, and this is not that easy. There are a lot of false positives in the literature. Things that we've tried up to now aren't very successful. So we've tried to replicate a lot of literature results. Unfortunately, we haven't been very successful in that. So yeah, it's a big challenge, I think.
Thank you.
Maybe a comment I can make on that part. We also have a nice interview together with Jote, the Journal of Trial and Error, where they are really boosting to share negative results. I think we are only used to share our positive, great inventions in scientific publications. But we all know that probably 80% or something of all our experiments don't end up in those publications. And are still something they are very valuable to prevent others to also waste their time to reproduce the same experiments. So please look into the Jote, the Journal of Trial and Error Research, and also try to stimulate the sharing of your negative results so that we can help each other preventing mistakes. Question from Martin.
Yes, hi, my name is Martin. I'm a PhD student at TU Delft. I just have a quick question about the slide where you showed that you can predict the selectivity of CO2 reduction. I saw that the selectivity was as a function of for single crystal catalysts. I'm curious, does this also translate to that you can predict CO2 reduction selectivity for polycrystalline materials?
Yeah, so DFT, of course, we have to go for sort of an optimal model system. Huh? So what we did here, so this graph, this is single crystal, so we are comparing single crystal electrodes with a 111. We did the same comparison with other surface geometries, and then you see that you get the same kind of classification. For DFT, it's more difficult if you would like to, of course, then model polycrystalline, because what is polycrystalline? Huh? So this is very difficult to, of course, to put into your method, because polycrystalline is not that well defined. Let's say it like this. So for DFT methods, we're trying to go for like these optimal model systems in that sense.
Cool.
Okay, thanks Martin for the question, and thanks Ruud for the nice presentation.